This is not recorded. No, sorry.
You have huge time savings because you are going to, the human will accept the proposal if it's correct, and it's much faster than searching the right code among 80,000 codes. And plus, it's also a problem to hire employees because this is they need to be skilled. They need to have medical knowledge, but then they need to perform a repetitive task. So this is difficult. And I bring it here, this use case, because this is most likely that all pharma companies are facing these problems here. And here we present our solution that we developed. So what does the data look like? So this is a sample of a true data. We have a reported term, that's the input of our algorithm. And then we need to classify, and then we have to classify that and map that to the actual correct terms in the ontologies. So here is the lowest level term, and this is a slightly more general code that we can associate that to. And all the requirements, regulatory requirements, are at this level, at the PT level. So here you see some challenges. So you have, for example, here you have some details that are in the input are not required because on-off you don't need it to get the correct classification. But for example, fempop here, you do need to have the correct classification. Or you have, let's say, acronyms that appear often. Or you also have misspellings in that regard. Or you also have specialized medical text. You see here hemangioma TH12, that's about the spinal hemangioma. So something very specialized that we need to capture. Plus, you do have paraphrasing. So just simply looking at and then looking at verbatim the terms will not work. So this is a sample of the data and the challenges that we see there. So the challenges are that we have text data, which is unstructured because they are medical terms. There are 80,000 in the lowest level granularity or 26,000 in the less granular version that each term can be mapped to. So it's very difficult. And making that even worse is that we have 80% of the classes of out of these 26,000 appear less than 10 times. So very few data points to train on for most of the classes. So we really need to have state-of-the-art AI and natural language processing methodologies. Plus, since the very beginning, we had the requirement to put this into production. Then I had to think about a scalable, reliable, and also automatic solution after deployment. So that was the bar quite high, admittedly, to make this successful. And so let's go to the actual AI algorithm deep dive. So here we see the whole procedure of the algorithm, and I'll guide you through the process that will go from the input to the classification. The first step, we had data sourcing, and then we just do some pre-processing, very little pre-processing. But what I do, and I found it very useful, is that since I show you that we have misspelling and rare data, then what I do, I create simulated data that are fake, but yet they are realistic, making misspelling, so that we can then train a bit on misspelling that we haven't seen before. And so this is turns out to help the accuracy. And plus there are some other technical details why this is important, because we use BERT and this is byte per encoding, and so this helps, but this is beyond the scope of this talk. But this is something that I do as data augmentation, and then we arrive at the core of the problem, that we have text, and the computer only understands number, not text. So we need to translate text to a vector in such a way that the meaning is preserved. And from that vector, then we arrive at the classification decision. So how do we go from the word to a vector? Then we use something called distributional semantic. I will just try to explain in a couple of minutes to give you some feeling about it. So how do you capture the meaning of a word? And this is a quote by a famous linguist: "You shall know a word by the company it keeps." So what does that actually mean? It means that you can infer the meaning of a word from the words that appear close by to it frequently. Let me give you an example. So you have 3 sentences here, and I blanked out a word here that is missing. So 26 minutes, 11 seconds is the word blank for the 10,000 meters from man. Second, oh no, I deleted the blank from the production database. That's something you might not want to do. Did you blank the meeting. Now, if you think about it a few seconds, then you will see that the word is actually a record, right? Because from the context, you can guess and figure that out. Plus, in these three examples, you see that the same word, that is the same letters, means different things according to the context. And this is what you want to capture to a very good model, and that's what this model is called BERT. It's context-dependent model, which is able to map from input to text to vector in a way that you can preserve the meaning and distinguish the various meaning of a given word according to its use. This is the same algorithm that Google claims is using their search engine. Very popular algorithm in NLP. So, but how does it actually work? So I just to give you a feeling. So what the idea is that you get input text and you mask some text. So you remove some text and then you train a neural network to complete the sentences, completing the words that you actually blanked out. This is an example. So the woman walked across the street, checking for traffic over blank shoulder. Now you can see that here you will put her. And the computer, like when it tries to let's say map that and say, okay, let's complete that, then he will learn something called co-reference, because it's her is about the woman, right? It's not his shoulder. That would be a wrong completion. Or here, I went to the ocean to see the fish, turtles, sails, and whales. So here, whales appear close to fish and turtles, so you can get a meaning of what whales is, right? And you can also learn higher level things. So overall, the value I got from the 2 hours watching, it was the sum total of the popcorn and the drink. The movie was awful, right? And this you can see that you can also learn higher level things. And yeah, this is the main idea of these BERT models. And since here we're talking about medical text, that I took the best performing model as July 2021. And these are all the references, PubMed, BioBERT, and ScioBERT, to do this mapping from a word to a vector. Now we have words that are represented as vector. We capture the meaning as best as we can with the state-of-the-art models. And now, how do we actually arrive to at the classification, right? Because we still have to pick the right class out of 80,000 of those. And so the way I frame this problem is slightly different than my previous colleagues on other literature. I simply frame this as a multi-class classification problem where each entry in the dictionary is a unique class. It's a bit radical, simple, and it turns out to work very, very well. So then you have that, so classification task. Then we have these embeddings that I already told you about, this specialized mapping for medical text. This is the input, the starting point, and then we need to do something called fine-tuning and training. So after this representation, we arrive at a classification model, and this is quite a GPU intensive, so computational intensive task that takes around 7 hours on 4 GPUs. It's not too much. We do it once a month. But it's some you need to have some let's say understanding of how GPU works and all of that. But this is the task, and this is how we arrive at the classification. And now we have one model, but we have a problem in one model, and the problem is that in AI and machine learning, when you have complex models, they according to the starting points of where you are, let's say the starting condition, you can have different results according to, let's say, the random seed that you start with. And this is something you don't want to have because you want to have a stable and reliable solution to put in production. So what I did, I combined different models, actually using this methodology called deep ensemble. So training different models, starting from different random seeds and averaging their probability distribution. And then arrive at classifications. You can look at the details there in the paper. We also have a paper. I'll share the details later. And so using these and combining this with deep ensemble has 3 advantages. The system is more stable because you have a lot of models that are voting, if you want. Then they are more, the improvement, the performance is better. And then also the uncertainty estimate is better. So this was a win-win for us, and that's what we did. And then to conclude, before I go to the results, so I evaluate the model uncertainty using something called predictive entropy, because if you read the literature, the probability that you get out of the classification model is usually not reliable. So I use this technique from some researchers before at Oxford and now at Cambridge. So this is and then at the end we arrive at the classification. Now let's give you some results. So before we had an in-house, so we had a vendor solution that arrived at the PT accuracy of 75% here. And now our internal solution arriving, combining different models, as just exactly as I showed you, arrive at the 92% accuracy, which is a very, very high accuracy. And this makes the proposal for system is live since January 2022, and it's making all the proposals for all clinical trials appear. So there's always human revising the proposal. The first proposal is done by our system. And so it's a big improvement on what we had before. And then one other thing that you want to think about is that I told you that we can estimate the uncertainty, right? So a good uncertainty will tell you when you are wrong in advance before you do know that you are wrong. So how do you evaluate that? There are different ways, but one interesting way from a business perspective is to say, let's take the prediction where you are most sure about. And here I took, let's say, the top 80% of the prediction where we are more sure. And then let's see if we actually do better. How is the accuracy there? And it turns out that for the 80% more certain data, and we can predict before knowing the right answer if you are certain or not, we arrive at a very high accuracy of 96.8%. And this is quite good because here we achieved the Holmes is the project name that of this internal system arrive already achieve the 95% accuracy that is required by our regulatory authorities for the whole medical coding process, so including the human intervention. So here the proposal for the most certain data already meet the regulatory requirement without a human. That said, the human is always there in Bayer revising our codes. And just to conclude, before I take question, if any, if time allows, we believe in sharing the knowledge. So I actually wrote a scientific publication on that, where you have all the technical details. There's also a new few-shot methodology that I proposed there that it goes even better, 92%, but we didn't put it in production because it's a bit involved. And this paper was just accepted today at the top NLP conference, and it will be available on the archive next week. And if you're open to collaboration, please send me an email, contact me on LinkedIn, and we're happy to discuss if this can be, we can collaborate on this solution. And yeah, that is all from my side.
Thanks a lot for this amazing presentation. Just one question, if we can take from Florian. Florian, I give you microphone for the question, please, shortly.
Yeah, quick question. Can you hear me?
Yeah.
Okay?
Yes.
Yeah, perfect. I was wondering, are you just doing English text here, or have you like also done multi-language? Is PubMed BERT multi-language or just English?
Yeah, good question. So we only do English because that's the data that we get as an input. So we are not interested in multi-language, but it's not a problem to adapt this framework to multi-language. You have three options there, not two options. You either translate the text that you get in, and then you apply English. So three options you have. That's the first option. Second option is to use a specialized model for a given, let's say, language, and that is the second that you can do, or you can even take a multi-language model, let's say, and that you could also try that one. But as far as I know, all the scientific text, I didn't know any scientific text. I didn't find any that are not in English, so that are available. But I think we had very good experiences with translating also medical text from different languages to English. So maybe that's the most pragmatic way then to apply then this methodology.
Thanks a lot. Thank you for the question and answering. The presentation was amazing. Thanks a lot, Angelo. That was a pity. Just the first 5 minutes was not recorded because of the networking coffee break time, but the rest of the